In everyday life, pure usually means a product that hasn't been tampered with. But in chemistry, a pure substance contains exactly one element or compound. It behaves predictably, like melting or boiling at a sharp, exact temperature. The liquids and powders we interact with daily are almost always mixtures. Substance is a mixture. Chemists use paper chromatography to physically drag the individual components apart. The mechanics rely on two phases. A solvent, called the mobile phase, creeps up a piece of absorbent paper, which acts as the stationary phase. Because different chemical compounds have different levels of solubility, the solvent carries them across the paper at different speeds, leaving a trail of separated spots. This chromatogram shows how chemists identify separated spots. By dividing the distance a specific substance traveled, say 8 centimeters for the green spot, by the 10 centimeters the solvent traveled, you calculate an RF value. Matching that value against known solvents identifies the unknown component. Chromatography proves that a substance is a mixture by pulling it apart. But separating the pieces is only the first step. Uncovering the specific chemical identity of those separated fragments requires a direct interrogation of the matter itself. Historically, chemists identified unknown substances by provoking a reaction and observing the results with their own eyes and ears. This is especially necessary when the byproduct of a reaction is an invisible gas. If you suspect a reaction is producing hydrogen, you introduce a burning splint to the mouth of the test tube. Hydrogen burns rapidly, creating a highly distinct squeaky pop. Other gases require visual confirmation. Oxygen will instantly relight a glowing, ember-tipped splint.
If you bubble carbon dioxide through a test tube of clear calcium hydroxide, the lime water reacts by turning milky and cloudy. Chlorine gas is highly reactive. Holding a piece of damp red litmus paper over a test tube of chlorine will rapidly bleach the paper completely white. These diagnostic tests represent chemical analysis at its most raw. The chemist is relying entirely on human sight and hearing to confirm activity they cannot physically feel or touch. When working with solid metal cations, chemists use extreme heat to force the elements to reveal themselves. By placing a metal sample on a wire loop and holding it inside a roaring Bunsen burner, the flame will ignite with specific colors. Lithium burns crimson, sodium flashes an intense yellow, potassium produces a pale lilac, calcium flares into a bright orange red, while copper turns the fire a vivid green. But relying on human eyesight immediately introduces a critical flaw.
If you are testing a mixture that contains multiple metals, the intense yellow emission of a sodium ion will easily mask the color of any other metal burning right next to it. The human retina is a biological lens, not a precision instrument. When overlapping light hits our eyes, our vision cannot reliably separate the true elemental signatures hiding inside the fire. If heat fails, chemists can dissolve the unknown sample in water and force the invisible ions to crash out of the solution as visible solid matter. Adding a few drops of sodium hydroxide achieves this by creating a precipitate. Transition metals form highly distinct colored precipitates. Copper produces a light blue solid. Iron 2 turns a murky green, and iron 3 creates a deep brown. Yet ambiguity strikes again. If you test solutions of aluminum, calcium, or magnesium, the sodium hydroxide will produce 3 identical white precipitates. To separate them, a chemist must carefully add excess sodium hydroxide to the sample. Out of the 3 identical white solids, only the aluminum precipitate will dissolve back into a clear liquid. These bench tests are beautiful, but they require subjective interpretation. Squinting to distinguish subtle shades of blue or green, or trying to separate multiple identical white powders leaves massive gaps for human error. To eliminate observational error, chemists bypass human senses entirely. They rely on instrumental methods like flame emission spectroscopy. When a metal solution is placed into a flame, the thermal energy excites the electrons in the metal ions. They jump outward into a higher energy level. When they inevitably fall back down to their original state, they release that absorbed energy as very specific wavelengths of light. A machine called a spectroscope captures those exact wavelengths and converts them into a line spectrum. It acts like a highly detailed, readable barcode for every individual element. This solves the masking problem. Even if multiple elements are burning at once, the machine isolates each overlapping signature. By measuring the intensity of the lines on the spectrum, the spectroscope calculates the exact concentration of the ions. Instrumental methods deliver 3 concrete advantages over manual testing. They process results rapidly, They can detect incredibly small sample sizes with high sensitivity, and they are mathematically accurate. Traditional bench chemistry gives us a dramatic, hands-on window into the elements, but to strip away the flaws of human observation and read the exact composition of matter, we have to let the machines take over.